Okay, hi everybody. Welcome back to the section 4.6 video. And in this video, we're going to take a look at our first example of using variation of parameters. So, how do I know I need to use variation of parameters right away and not undetermined coefficients? Well, that's because right here, this cosecant of 3x, this is not a finite product or sum. Okay. Because cosecant, well, what's that the same as? It's the same as 1 over sine 3x, which is not a product, it's a division. So here, I would need to use variation of parameters. So here, I'll put an arrow. Uh, Need to use variation of parameters. Okay, so let's go ahead and get started with that. So the first thing you always want to do with variation of parameters, you always want to solve the constant uh, coefficient component. So we have 4y double prime plus 36y equals cosecant 3x. So remember that this component on the left-hand side is our homogeneous component. And so from our homogeneous, we are able to obtain our complementary solution. And my cosecant 3x is my non-homogeneous component, and that's where I get my particular solution. So let's go ahead and solve for this complementary solution. So I like to start this off with just a general solution heading, and then we'll say step one, solve the complementary solution using the auxiliary equation. And that comes from section 4.3. Okay, so we have the homogeneous component. That's 4y double prime plus 36y equals 0. And just remember the standard form for these constant coefficient homogeneous differential equations looks like this. Okay, so that means I have A equal to 4, B equal to 0. There's no y prime there. And C equals 36. So my characteristic equation would be 4m squared plus 36 equals 0. Okay, so now I want to solve for my roots. I want to solve for m. So 4m squared equals negative 36. M squared equals negative 9. M equals plus or minus the square root of negative 9. And what that comes out to is just plus or minus 3i. Okay, so just remember the form of solutions for complex roots is m equals alpha plus or minus beta I. All right, and so here I don't have an alpha, it's just plus or minus 3i. So that means here, like there's a 0 here. That means that m equals, excuse me, not m. That means alpha equals 0 and beta equals 3. Okay, those are our complex roots. because the solution to complex roots for my characteristic equation is y equals e to the alpha x times c1 cosine of beta x plus c2 sine of beta x. Okay, so my complementary solution is e to the 0x times c1 cosine of 3x plus c2 sine of 3x. And e to the 0 is just 1. So my complementary solution is just c1 cosine 3x plus c2 sine 3x. Okay, so that is my complementary solution. So step one done. Step two now is to, before I start my process, is to make sure my differential equation is in standard form. So step two, I want to get y double prime naked, meaning get into standard form. So let's write it like this. I'll say get into standard form, differential equation into standard form, meaning get y double prime naked. Okay, so that's step two. Let me write step two. So step two, all right, great. So let's go ahead and get started on that. So we have our differential equation. Let me just rewrite it. We have 4y double prime plus 36y equals cosecant 3x. So I want to get y double prime naked, so I need to clear out 4. I need to divide 4 to both sides. So my new differential equation will be y double prime plus 9y equals cosecant of 3x divided by 4. Okay, and so now this new function on the right-hand side, since we put in the standard form, this function right here, cosecant 3x over 4, this is my input function. And so what that means is that it is f of x. So that's going to be my function f of x when I figure out what my u1 and u2 are in my variation of parameters. So we'll just say f of x equals cosecant 3x over 4. Okay, so that's step two. We'll just leave it at that. Step three is now, officially saying what our guess is for our trial particular solution. So step three, we'll say make a guess for the particular solution. But when we do a guess for our particular solution within variation of parameters, it will always be u1, y1 plus u2, y2. And this is always our guess for variation of parameters. Okay, that's always our guess. So undetermined coefficients, we had to go back and see what is it like AX plus B. Is there a trig, is there exponential? But variation parameters here is always U1 Y1 plus U2 Y2. Okay, so that makes that step easier for us. Now the hard part is calculating what U1 and U2 are. Luckily, we have formulas, so let's go ahead and try that out. So step four, we'll say get U1 and U2. Okay, so U1, if you look at your formulas from the previous video or previous page, we know U1 equals negative integral of y2 times f of x, all divided by the Wronskian of y1 and y2, and that's all needing to be integrated. Okay, so this component right here, Wronskian, I have y2, I have f of x. I need to figure out what the Wronskian is. So y1, y2, maybe we didn't clearly state what those were, but if we come back up above, because we haven't really said, y1, y2 previously, but yeah, this c1 cosine 3x is y1, and this is y2. So we'll say y1 equals cosine 3x, y2 equals sine 3x. So that's where we get our y1 and y2 from. So let's go ahead and use these to get our Wronskian. So first, we need to compute the Wronskian. Okay, so the Wronskian would be y1, y2, and so we would have the determinant. My y1 we said was cosine 3x. Cosine 3x, and my sine is my y2. And so the derivative of cosine is negative sine, excuse me, negative 3 sine 3x. And the derivative of sine 3x is 3 cosine 3x. Just be careful with that chain rule. And so the determinant would be 3 cosine 3x times cosine 3x would be 3 cosine squared 3x minus negative 3 sine squared 3x. Okay, so two negatives make a positive. We end up with 3 cosine squared 3x plus 3 sine squared 3x. And we could factor out a 3. This is cosine squared 3x plus sine squared 3x. Let me clean this up. And cosine squared plus sine squared, well, that's our very old friend trig identity. That just equals 1. So this is just 3 times 1, which just equals 3. Okay, so the Wronskian equals 3. Okay, so let's go ahead and figure out what U1 is. So now we have all our components. U1 equals negative integral of y2. We said y2 was sine 3x right here. Excuse me, no, right here, sine 3x. And so let's put this in our integral. So sine 3x times our function f of x, which is cosecant 3x over 4. Okay, so cosecant 4, excuse me, cosecant 3x over 4, all divided by the Wronskian, which is 3, and then dx. Okay, so we have a couple constants we could take out. We could take out that 1/4 and that 3. So this could be negative 1/12 outside times the integral of sine 3x times cosecant of 3x dx. Well, what is the same as cosecant? Well, the same of cosecant is 1 over sine. So this is actually 1 over sine 3x dx. And so the signs cancel out. And so we just have an integral of dx. And the integral of dx is just the same as if you just have a 1 right in front. The integral of that is just going to be x. So this is just negative 1/12 x. And so u1 equals negative 1/12 x. Okay, so typically with variation of parameters, when you're trying to get U1 and U2, there's always one integral that's harder than the other, and this one would be the easier integral to compute. So I'm assuming the next one, U2, would be the harder integral to compute. But let's go ahead and try it out. So U2 is the integral of y1 times f of x over the Wronskian dx. Okay, so y1, let's kind of backtrack, is going to be this cosine 3x. So let's take that y1, let's come back down here and figure out u2. So this would be the integral of cosine 3x times that cosecant of 3x over 4, all divided by 3 dx. Okay, so let's take out the constant again, 1/12. So I'm left with cosine of 3x, and I'm just going to change this to 1 over sine 3x right away. Okay, so how would I solve this integral? Nothing really cancels out. We need to figure out a way to integrate. And here, what can recognize is that this is going to be a u sub. So u would be that sine of 3x. Du would be that 3 cosine of 3x dx. Be careful with the chain rule. And so I'm just going to move over that 3 and have cosine of 3x dx. So here I'll say u sub. Okay, so what we want to do is substitute correctly and then want to substitute correctly and solve for U2. Okay, 1 second, sorry. All right, so when we substitute, we get 1/12 times the integral of 1 over u times du over 3. We could take out our constant, 1 over 36 times the integral of 1 over u du. And this would be 1 over 36 ends up being natural log of u. Okay. We don't need constants here in variation of parameters in case you were wondering that. Uh, doesn't matter in this situation. So this would be 1 over 36 natural log absolute value sine of 3x. So maybe let me bring this down here. Okay, so u2 equals this. All right, so let's put this all together now. So what step were we on? We were on step 4. So we can call this step 5 now. Um, our particular solution, y sub p, or, we could say plug in y1, y2, u1, u2 into our particular solution. So remember our particular solution is u1 times y1 plus u2 times y2. And so our particular solution would be 1 over 36, excuse me, wrong one. It would be negative 1/12 x times y1, which is cosine of 3x, plus u2, which was 1 over 36 natural log absolute value sine of 3x times u2, which was sine of 3x. Okay, and now step 6, we can call it, step 6 is form the general solution. And so our general solution is complementary plus the particular. Here's our particular. All right, our complementary is way up here, way at the beginning. So we just take these, add them together, and that's our general solution. So y equals c1 cosine of 3x plus c2 sine of 3x minus 1/12 x cosine of 3x plus 1 over 36 natural log absolute value sine of 3x times sine of 3x. And that's our solution. Or I'll circle this to give it some distinction. But that's our solution. Okay, so A very long problem, lots of moving parts, but same thing, solve complementary and solve our particular with this new method we just learned. Okay, so that's it for this video. Thank you for watching. I'll see you in the next one. Take care.